It looks like a simple process, but it's actually a really complex challenge to automatically spot anything hidden that shouldn't be there.
Yeah.
Even a tiny, cleverly concealed item can be a significant risk.
Absolutely. And what makes it so tricky is, well, the visual clutter, you've got all sorts of overlapping items packed together.
Right.
And unlike a regular photo, X-rays give us these grayscale images where, similar materials can look quite different depending on how they're oriented or positioned. It's a tough task for a human, let alone a machine.
And that's exactly what we're diving deep into today. We've got some fascinating new research that's exploring how advanced artificial intelligence is tackling this problem, this whole finding hidden objects in X-ray scans thing. Think of this as your fast track to understanding some pretty cutting-edge science.
Yeah, our goal in this deep dive is really to understand how different types of AI brain, we call them network architectures, how they perform when they're analyzing these complex X-ray security images.
Okay. We'll be focusing on the strengths of different approaches, and our main source is a recent research paper that's just full of experiments using real X-ray data.
So in the world of AI that looks at images, there are generally two main approaches, right? First, you have convolutional neural networks, or CNNs.
Yep, CNNs.
Imagine these as being really good at seeing small, local details, like the specific shape of a prohibited item, for instance.
Exactly. Very good at pattern recognition on a small scale.
Then you have transformers. These are maybe better at understanding the bigger picture, the context of how different objects in the scan relate to each other.
Right, the global relationships.
Now, when it comes to security X-ray analysis, the field has, well, historically relied quite heavily on CNNs.
That's right. CNNs have been the go-to for a while because they're just really good at learning those visual patterns in images. But the exciting development recently has been in combining these two strengths. Okay, here's where it gets really interesting. This new research asks a really crucial question. How do these newer hybrid AI systems, the ones that combine the local detail focus of CNNs with the broad context understanding of transformers, how do they compare to the traditional CNN-only methods when it comes to actually detecting illicit objects in those X-ray images? It's essentially a competition between different AI strategies.
And to understand why this competition is important, let's think about those fundamental challenges of X-ray security again. As we mentioned, it's not just about recognizing a single object in isolation.
Right.
The paper points out issues like occlusion, where objects are hidden by others. Then you have the cluttered scenes, just stuff everywhere. Plus, the same type of object can look very different in an X-ray depending on its position or even what it's made of sometimes.
Yeah, that variability must be tough.
It is. And finally, the grayscale nature of the images means we lose all that color information that our own eyes rely on so much.
It's like trying to pick out a specific shape in a big pile of gray shadows. It's hard. Now let's talk more about those traditional CNN approaches. As you said, they've been dominant.
For a good while.
And the paper gives us a sense of that history by mentioning a whole range of different CNN-based methods adapted for X-ray. We're seeing names like DOAM, LIM, and the very popular YOLO family, things like YOLO 3, YOLO 5.
Yeah, YOLO's huge in object detection.
Even some versions specifically tweet for X-rays like EM-YOLO and SC-YOLO 8 and, a more lightweight option called Tiny Ray. So it sounds like CNNs have been really, really heavily explored in this area.
Oh, absolutely. These CNN-based methods have made, significant progress in automating X-ray object detection. People have been continually improving them to better handle the unique aspects of X-ray imagery. However, the field of AI is always advancing, right?
Which brings us neatly to the rise of transformers. Now, we're not talking about the robots from the movies here.
No, not those.
But vision transformers, or VITs. These are designed to understand the global context of an image using something called self-attention.
Self-attention, yeah.
Can you maybe explain that a bit? Like, think of self-attention as a way for the AI to weigh how important each part of the image is in relation to all the other parts when trying to understand the whole scene.
That's a good way to put it. It allows the model to look at the entire image simultaneously and figure out which parts are most relevant to understanding other parts, even if they're far away from each other in the image. The paper mentions some key advancements here, like DETR, sparse DETR, and DINO, which have really shown what transformers can do in object detection.
So it's a fundamentally different way of processing the image compared to CNNs.
Exactly. CNNs tend to look at small patches, small areas, and gradually build up an understanding. Transformers can sort of grasp the whole scene structure at once.
And then you get these hybrid CNN transformer architectures. It's the idea of getting the best of both worlds, isn't it?
Pretty much, yeah.
The fine-grained detail recognition of CNNs, combined with the ability of transformers to understand those long-range connections and the overall context.
The thinking is that this combination could lead to even more accurate, more robust object detection.
And the paper specifically mentions one called Next-ViT as a leading example of a hybrid architecture that's also designed to be efficient, which is important.
Efficiency is key, yeah.
The researchers point out that while these hybrids are showing great results on, like, regular photos, they haven't really been thoroughly investigated yet for security X-ray imaging.
And that's precisely the gap this research aims to fill. They've set up this series of experiments to really put these different AI architectures through their paces on X-ray data.
Okay, so let's get into the specifics of the experiment. What did they actually test? The researchers evaluated a few key AI architectures. They started with a really solid foundation, a traditional CNN-only model.
The baseline.
Yeah, the baseline, which was U11.8 using what's called its CSP DarkNet 53 backbone.
Right. Think of the backbone as the initial processing part of the AI, the part that first looks at the image and extracts key features. YOLO8 with this backbone is a well-established and high-performing CNN-based object detector, so it provides a really strong benchmark to compare the newer approaches against.
Makes sense. Then they looked at several hybrid architectures. Now, these combine different backbones again, that initial analysis part, with different detection heads.
The detection head is the part that makes the final call, right? Where the objects are and what they are.
Exactly. So one hybrid they tested used the YOLO8 detection head, but instead of its usual CNN backbone, they swapped in Next-ViT, that efficient hybrid we mentioned.
Okay, so mixing and matching.
Yeah. And they even experimented with a few different ways of connecting these two parts, using something called skip connection configurations. They tried C10, 20, C9, 19, and C7, 17.
Ah, the skip connections. Those are important for passing information between layers.
Right. And interestingly, they found that the C7, 17 configuration performed the best for this specific combo. It's like finding the best way for the different parts of the AI's brain to talk to each other.
Optimizing that information flow between the local details and the global context.
They also experimented with a different type of detection head called RT-DETR, which is based on transformer technology itself.
Okay, so a transformer-based head now.
Yeah. They paired this RT-DETR head with two different backbones. First, a CNN called HGNet V2, creating another kind of hybrid system.
Right, CNN backbone, transformer head.
And second, they paired it with the Next-ViT hybrid backbone again.
Okay, so hybrid backbone, transformer head.
And just like before, when they used RT-DETR with Next-ViT, they tested those different skip connection configurations, C10, 20, C9, 19, C7, 17, and found that C9, 19 worked best in that case.
So quite a bit of detailed architecture comparison going on. We have a purely CNN approach, then hybrids using a CNN head with a hybrid backbone, and other hybrids using a transformer head with either a CNN or a hybrid backbone. Good variety.
Definitely. Now, to really challenge these AI systems, the researchers used 3 publicly available X-ray data sets, and each one has its own unique difficulties.
Right. The data matters hugely.
The first one is called EDS. What's special about EDS is that it contains X-ray images taken with 3 different X-ray scanners.
Ah, okay. That's important.
This introduces what they call a domain distribution shift, essentially. The images from each scanner look slightly different.
Different characteristics, yeah.
The dataset includes 10 classes of common everyday objects, and the experiment involved training the AI on images from one scanner and then testing it on images from a different one to see how well it could adapt.
That's a really crucial test, isn't it? Because in the real world, you will have different machines, and AI needs to be robust to that.
Exactly. The second dataset is X-ray. This one contains actual airport X-ray scans, and the objects in these scans, there are 8 classes of prohibited items, were identified and labeled by real airport security personnel.
Okay, so real-world airport data, labeled by experts, that gives it credibility.
And it's divided into standard training and testing sets.
Got it.
Finally, they use PI-DRE. What makes PI-DRE particularly interesting, I think, is that it focuses on items that have been intentionally hidden.
Oh, simulating concealment. That's tough.
Yeah. Trying to mimic real-world tactics.
Sure.
It includes 12 classes of prohibited items and is also split into training and testing sets. But the test set is further divided into easy, hard, and hidden subset.
And that hidden subset must be the real challenge.
Exactly. That's the one with the deliberately concealed objects, where occlusion is a major factor.
So the AI has to find things even when they're buried under other stuff. Very realistic.
Now, to see just how well these AI architectures were performing, the researchers used a couple of key metrics. MAP50 and MAP50.95.
Standard object detection metrics, yeah.
And
MAP is mean average precision.
right, and the 50 and 50.95 refer to the intersection over union, or IOU threshold.
Mm.
You can think of IOU as a measure of how much the AI's predicted box around an object overlaps with the actual box.
Mm-hmm.
So MAP50 uses a threshold of 50% overlap, kind of lenient. But MAP 50.95 is much stricter. It averages the performance across overlap thresholds from 50% all the way up to 95%.
So a higher MAP 50.95 score means the AI is not just finding the object, but it's pinpointing its location really precisely. It's a much tougher measure.
Exactly, getting the box just right.
Yeah.
Okay, so the moment of truth. What did they actually find? What were the main insights from all this testing?
Well, the overall result was maybe a bit surprising, actually.
How so?
On the Hicks-ray and PI-DRE datasets, remember, those are the ones with more consistent data from specific sources, the traditional CNN-only setup, that baseline YOLO with its regular backbone.
Yeah.
It generally showed the best performance overall.
Really? The old guard still holds strong.
It seems so in those conditions. The paper suggests that CNNs are still exceptionally good at recognizing those specific visual patterns in X-ray images, especially when the images come from a consistent source, like a single type of scanner or setup.
So the hybrids didn't just blow it away?
Not on those data sets, no. It shows that for consistent X-ray image types, traditional CNNs are still incredibly effective.
Okay. But I sense a but coming.
Hey, yeah, there's definitely a but. Here's where it gets really interesting. There's a really important exception. On the EDS dataset,
The one with the different scanners, the domain shifts.
exactly that one. On EDS, most of the hybrid CNN transformer detectors actually performed better than that CNN baseline.
Okay.
And specifically, the hybrid using the RT-DETR detection head with the HGNet V2 backbone, that one showed the best performance on average across those more challenging domain-shifted conditions.
So the hybrids shine when the data gets messy, when it varies.
That seems to be the key takeaway here. This is kind of the aha moment. The paper concludes that transformers, with their ability to understand the overall context, seem to be more resilient, more robust when the characteristics of the data change. They adapt better to those differences between scanning machines.
That makes sense. So for real-world deployment with mixed equipment, hybrids might have a real edge.
That's the implication, yes. They could offer more consistent detection across different environments.
What about comparing the different types of hybrids? You mentioned the YOLO head versus the RT-DETR head.
Right. Another interesting point. Across all the experiments, when they used the same backbone, that Next-ViT hybrid backbone, the YOLO detection head consistently performed better than the RT-DETR head.
So the CNN-based head beat the transformer-based head in the hybrid setup.
In this context, yes. The researchers suggest that maybe those transformer-based detection heads like RT-DETR might not be quite as well suited for X-ray images. They theorize it might be because objects inside bags often don't have a predictable spatial arrangement,
Unlike cars on a street or faces in a crowd where there's more structure.
Exactly. It's just stuff packed in. That lack of consistent spatial structure might favor the way the YOLO head works, even within a hybrid system.
That's a really subtle point. It's not just about slapping components together.
Definitely not. And that leads to another finding. Just swapping out a CNN backbone for a hybrid one wasn't a magic bullet either.
Oh?
Yeah. The researchers found that simply replacing the backbone with Next-ViT, whether it's in the YOLO system or the RT-DETR system, didn't always lead to improved performance.
So it depends on the combination.
It really seems to. It emphasizes that you can't just, mix and match the latest AI components and expect them to work perfectly. You need careful design, careful testing to ensure the backbone and the head are actually compatible and work well together for that specific task, in this case, X-ray object detection.
It really highlights the complexity involved in building these systems. It's not plug and play.
Not at all. It requires a deep understanding of both the architectures and the data itself.
Okay, going back to the results on that challenging EDS dataset for a second. You said the hybrids generally did better. Was the CNN baseline consistently worse there?
Pretty much, yeah. The paper states the CNN-only model showed inferior performance across all the different train-to domain shift scenarios they tried. It really reinforces that idea that the hybrid architectures offer better robustness when dealing with those inconsistencies in the data source.
That robustness seems like a major selling point for hybrids then.
It's a critical advantage, especially if you're deploying systems across a wide range of locations or equipment types.
What about on PI-DRE, the one with the hidden items? Did they break down the results for the easy, hard, and hidden subsets?
They did. And it was interesting. The CNN baseline EM-YOLO actually performed very well on the easy and hard subsets. Still very strong there.
Okay.
But on that really tricky hidden subset where objects were intentionally concealed,
Yeah.
the hybrid model using the EM-YOLO detection head and the Next-ViT backbone actually showed a slight improvement, just a slight edge, but it was better at recognizing those deliberately hidden items.
Huh. So maybe the hybrid's ability to see context helps it find things that are obscured.
That's the suggestion. It hints that these hybrid approaches might have an advantage in those really challenging real-world scenarios where people are actively trying to hide things. Maybe understanding the surrounding context helps it pick up on subtle clues.
That makes intuitive sense. Did they look at specific types of objects, like were the models better or worse at finding certain things?
Yeah, they did drill down into that, referencing Figure 3 in the paper.
Yes.
On Higgs-ray and PI-DRE, the more consistent data sets, the CNN DRIS line generally outperformed the others across pretty much all the different object categories.
This is dominant there.
Yep. But on EDS, with the domain shifts, the CNN baseline did worse on almost all the object types compared to most of the hybrids.
Oh, wow.
And this difference was particularly noticeable for things like plastic bottles, scissors, lighters, power banks, and pressure containers.
So the hybrids were significantly better at spotting those specific items when the scanners changed.
Exactly. It gives us more specific clues about where the architectural differences really matter under those varying conditions.
What about the size of the objects? Did that play a role?
It did, particularly on the EDS dataset again. They looked at performance based on object scale, referencing Figure 4.
Yeah.
On EDS, the hybrid models, especially the DLF8, Next-ViT, and the RT-DETR HGNet V2, performed significantly better than the CNN baseline for medium-sized objects.
Medium-sized, interesting.
Yeah. But this performance gap decreased for larger objects. For the really big stuff, the difference wasn't as pronounced.
Huh. Any idea why?
The paper doesn't speculate too much, but perhaps the combination of context and detail in hybrids is particularly advantageous for resolving ambiguity around medium-sized items when the image characteristics shift. Larger items might be easier to spot regardless.
And what about on the other data sets, Higgs-ray and PI-DRE? Did size matter there?
Interestingly, no. Object size didn't seem to be a major factor affecting performance for any of the models on Higgs-ray and PI-DRE.
So that size effect seems linked to the domain shift challenge specifically.
It appears so, based on these results. It adds another layer of understanding to where these different architectures excel or struggle.
And the paper also includes visual examples, right? Like pictures of the detections.
It does, yeah, in Figure 5. It shows examples of the detection results from the different models across the beta sets. We can't show them here, obviously, but they visually illustrate the kinds of differences in performance, like missed detections or inaccurate boxes between the models.
Right. Helps to actually see it. Okay, so let's try and wrap this up. If we bring together the key findings from our deep dive into this research, what's the main story?
I think the main story is one of nuance, really. We see that these hybrid CNN transformer architectures show significant promise for improving X-ray security, especially, and this is the key part, especially when you're dealing with variations in the scanning equipment and the data itself, that domain shift problem.
Right. In those messy variable situations, they seem more robust than the traditional CNN.
Exactly. They seem better able to adapt.
But it's not like hybrids just won across the board.
Yeah. No, definitely not. The research also clearly showed that in more standardized environments where the X-ray images are consistent, those traditional CNN architectures, like the EM-YOLO baseline they tested, can still be very, very effective. They even held an advantage in some cases on those data sets.
So context matters. The type of data and environment you're working with is crucial.
Absolutely. And it's also really important to remember that nuance about the components within the hybrid. The choice of the detection head, for example, mattered significantly.
Yeah, the EM-YOLO head generally beating the RT-DETR head in these tests.
Right. It just highlights that simply combining architectures isn't a guaranteed win. You need careful design, careful integration, and a real understanding of how the parts work together on this specific type of data.
So no silver bullet, but promising directions. Does the paper suggest where research goes next?
It does. It points towards further exploration, looking at different hybrid configurations, maybe different ways of combining CNN and transformer features, and definitely evaluating these approaches on more data sets, maybe even larger or more diverse ones.
So the investigation continues.
Oh, yeah. It's clearly an active area of research, and you can see the potential for real advancements in security tech down the line.
Okay, so here's something to really think about as we finish up. Considering, the increasing sophistication of security threats, and also the sheer variety of places where X-ray screening is used now. It's not just airports, right? It's courthouses, mail facilities, cargo screening.
Borders, critical infrastructure.
Exactly. So considering all that diversity, how might these insights that we've discussed, the strengths of hybrids and variable conditions, the continued strength of CNNs and others, the importance of the right components, how might all this shape the development of security systems that are, well, more adaptable and more reliable in the future?
That's the big question, isn't it? How do we leverage these different architectural strengths to build the best possible defense for each specific situation?
It really makes you consider the path forward for innovation and keeping us safe. Lots to think about there.